Thanks all for being here. I'm just going to give a quick talk about our new SmartNICs, which are now on OCP form factors, and how we can use them to reduce latency, both in single host and multi-host cases. It's going to be pretty simple, pretty high level, and the the examples I'm going to be giving are going to be pretty fluffy. I'm not going to try and go into too much detail here today. Firstly, I'll just quickly run through exactly what we're doing with OCP, how we're helping, how we're contributing, and I'll give you everyone Jack's email address in the back corner because he's the guy doing the real work. And then we'll quickly just explain actually what's on this chip that's sitting on this thing, and then go through explaining very briefly why people have issues with latency and what actually happens and how you can try and fix them. And then we'll just quickly run through how SmartNICs can actually help, both in the single host and multi-host cases. It's not going to be in any great depth today. If you want more detail, just come and grab me afterwards. So firstly, what do we have? So we've got the first, this is a 25 gig example, but we've got the first 25, 50 gig SmartNIC on OCP MES2. Now this thing's fully programmable. It's got 72 cores on here. Each one of those cores is 8 threads. And the reason we can put it on MES2 is because of power. So we can get, this is down to about 15 watts, depending on the use case. It can head up to 25. It's up to about 25 if you're using a lot of DRAM and you are doing a lot of external memory lookups. So that's kind of how the power profile sits. And that's, I think, quite a big thing because a lot of sort of SmartNICs that kind of are out there are very, very useful, but they require significantly more power. So really what we've tried to do is make something which really fits within that OCP form factor and sort of power envelope. And we're currently contributing to MES-v3. That's Jack in the corner I pointed out to you guys earlier. Everyone take his email address and flood him with emails, please. Just a quick run through actually what the SoC architecture is on the NIC. So the 72 cores I mentioned are small flow processing cores. They're specifically designed for networking. So their instruction set is designed for networking. And the way they're set up is designed for networking. So you've got a lot of registers for each one of those threads. But you've also got a transactional memory architecture, which I'll go through in a second. So really the way we've structured it is that you've got these, the islands, which are called the ME islands. Those are the ones where the actual flow processing cores sit. Then you've also got crypto. You've got internal memory units. You've got external memory units. You've got an ARM there for a control. And you've also got other hardware accelerators sitting around the outsides. And crucially, obviously, for the multi-host case, you've got 4 different PCIEs, which can be used to route packets to 4 different hosts. Oh, one of the other things I should mention before I jump off this slide is that the reason this is all possible is because of the fact that there's an extremely high-performance interconnect, which basically mesh, which sits underneath this whole thing. That bus is what allows us to be able to pass information very, very, very quickly through between different cores, which allows us to use this sort of many-core model. It's not really even a multi-core model, it's a many-core model, because you've got a lot of interactions happening and about 500 packets potentially being processed at the same time. So it's kind of like a cross between an old-school CPU and a GPU. This is just to give you a quick example of the transactional memory architecture, which is how the silicon works. You've got a bunch of local memory, and then you've also got further out, you've got on the island, which are those ME islands I identified, you've got 2 separate chunks of memory sitting there, and then externally on the IMEM, you've got about 4 to 8 megabytes there, times that by 2 if you have 2 IMEMs, and then also you've got EMEM, which is between 2 and 8 gigabytes. Now, how do you hide all these transactions? If you've got 500 packets, trying to look for different bits of memory at once, you're going to run into some fun when you're actually trying to architect how those threads are going to work with each other. So that's done by the cooperative multi-threading model, which is why you have 8 of these threads on each one of these processors. That's really how you're able to get the speed up and how you're able to hide the latency, because there's always a packet which requires processing. While one guy's busy looking up, another packet's being processed. And they all interleave, and you tend to actually end up with very few wasted cycles. So and this is going to be very high level, guys. This is just quickly, why is latency an issue? Why is this a problem which people run into in the data center and in telco networks and other places as well? So very simply, we're just going to talk about a little bit of TCP and quickly what latency actually affects. So very obviously, if you've got large amounts of latency, your throughput's going to go down. The reliability of your remote procedure calls is going to go down. And finally, it's just a factor of network hygiene. If you have lots of latency, and that means that you've got less, actually you're using your pipes less well. There's potentially going to be more issues in switches, having to deal with packets, and there's lots of pain points there. I just want to shout out to a very simple little tool, which I played with a bit actually, to get some of the sort of results. So if you want to just play around with that and understand how latency affects your network, it's actually quite useful. Just again, TCP 101. Three very simple factors that are going to affect your throughput. Window size, losses, and latency. Window size, if you've got a very large TCP window size, then great, you've got a lot of packets in flight, you're looking for one ACK, a lot of packets in flight again. That means you're using your pipe more of the time. If you have latency, it's exactly the same thing, but the other way around, because there's more latency between you sending out the window and you actually getting the ACKs back. That means, again, that you're using less of your pipe. And the third one, very simply, is just loss. If you've got losses happening, then you've got less good put. You've got packets, you're using your pipe for things which you don't actually get the other end. So it's just plumbing. 3 different ways of actually just losing packets. Well, not losing packets, losing throughput. So really, fundamentally, what latency does is reducing latency just increases your robustness. This is very simple stuff. Just wanted to make sure everyone's clear. One example I wanted to give, which is a little bit more depth, is just remote procedure calls. This is becoming more important, especially on the edge, where people are starting to look at applications like VR, AR in the future. And here, really, your sort of tail latency becomes quite important. If you have a large tail latency, and you've got a sort of disaggregated process which is using 100 nodes, the important latency for you is your P99 latency. The last percentile is actually the one where you're going to be running into trouble. Because with that last percentile, that's where 1 out of the 100 of those results will come back in that time frame. So it doesn't matter that the other 99 have come back. If you need all 100, then you're going to run into some issues. So just very, very high level, these are the kinds of problems people face. Now, how can we use SmartNICs to help? The example I'm going to give is, again, pretty simple. Just there's a million different ways you can do this. There's a million different ways to skin this cat. And there's certainly many other ways we're skinning this cat as well. But this is just the one example I wanted to give. So one of the problems you run into when you try and use something like a SmartNIC, and this is a problem I think which a lot of people have today, maybe not some of the largest companies, but if you're a little bit smaller, you don't have the resources yourself to be able to write complex applications, whether that be in FPGA code, whether that be in our version of C, whether that be in any sort of special proprietary SDK. You want to be able to just plug the thing in, use Linux, and offload stuff, because that's going to make your life a lot easier. So one of the things that we thought about was how can we use something like this, which is a fully programmable core, within Linux, and actually use that in a way that people don't have to go outside. And this is very much a software question, I realize. But people don't have to go outside what they are fundamentally trying to do in software. So that's why we got to EVPF, which I'll just quickly explain. So it's a small kernel-based virtual machine, which people use for filtering, load balancing, and a bunch of other types of applications, and it sits within the Linux kernel now. Now that then gets used for processing on different layers within the kernel. But this small virtual machine fits very well with our architecture, because the instruction set is incredibly similar to our instruction set, because, surprise, surprise, it was designed for networking. That means that we get significant advantages from just simply taking this, JITting it, the same way it JITs in the host, to our NFP. So this is what we have upstream Analytics. I think this is a laser pointer, yeah. So your usual path is, and this is being used by people out there today, you write your BPF program in C, it goes through the LLVM compiler, then there's a verifier in the kernel, which checks that the program is safe, and a JIT in the kernel, which just jits it down and it runs on your host CPU. Very low level, very high performance. Problem is, sometimes that isn't quite enough. So now what we've done is we've upstreamed a JIT, so you can actually, just using the kernel and using LLVM and the verifier, you can actually push code onto the NIC. So you don't need SDKs, you don't need anything else, you just plug the thing in and you just have Linux. Now, I'm just going to quickly run through two very, very simple examples of how using this kind of thing can improve latency. Now, obviously, there's throughput questions as well, and if people are interested in throughput numbers, I can show them at the end, but I'm just going to focus on latency for now. So the first experiment we did was just very simply take a small BPF program which just returns the ping packets. So you just ping the NIC and return the packet. We ran that program in the driver, so on the other side of PCIe, and we ran it offloaded in the NIC. This is what we get. So this is one of the things I found very interesting is the variance. So you can see when we're running in the NIC, it looks like it's pretty much exactly the same every time. This is one of the key things we found when we were looking at this stuff. The latency of processing is usually pretty much the same. We're talking, at a very, very small variance. And remember what I was saying about the remote procedure calls? If you look at what you're doing when you're doing things in the driver even, then you get a lot more latency variation. And that's because you're going across PCIe. There's a lot of effects there. There's a lot more wheels in the cog. Cogs in the wheel, wrong way around. And then obviously this is if you're running actually in the driver in the host. And then this is if you're running the actual standard ping, which is much further up the stack. So this latency is your kernel stack. This is your PCIe. And that's obviously something we thought was quite interesting, the fact that you create a much more consistent setup. The final thing I wanted to go through was we then did another experiment. Now, one of the things obviously with multi-host servers is that you've got a small PCIe by 2 or by 4. So you really want to use your PCIe as efficiently as possible. So what we did was we looked at situations where you have potentially aggressive traffic coming in, such as DDoS. And what we did was we basically flooded the server. We limited the PCIe to by 4 or by 2, flooded the server, and tried to filter out the correct types of traffic and only let through what we wanted to let through. So we built a very simple BPF program. All it does is filter out the non-ping traffic and load balance this and sends it back up to the switch where I was just dropping it in the switch. So this wasn't actually just dropping the packets in the NIC, it was actually taking them, allocating other servers for them, encapsulating them and sending them back out on the network. So effectively dynamic load balancing. And with this case, this is what we saw. So this is when we're just simply comparing running it in the driver, running it offloaded. So you can see in this case, when you've got a PCI link under stress, then you end up with a very, very significant latency reduction. And at this point, the variance we were seeing earlier, so you'll see, oh, look, it looks much more smooth now. Now, the reason for this, I believe, is the fact that the numbers here are so much bigger that the variance actually doesn't show up as much. So that was really all I really wanted to go through today. It's very, very simple. And the focus really is that there's a lot of ways that you can skin this cat. There's a lot of ways you can use this stuff. But what we need to understand today is, and really what I wanted to sort of start driving a conversation towards is, this is kind of a crossing point between hardware and software. And at the moment, it's hard. It's not something which is well handled. There's not the infrastructure out there today that you see with a lot of the other types of devices you have out there. We started getting, switch operating systems. We saw a lot of great talks, about Sonic and so only over the last couple of days here. You see a lot of, hardware standards being driven very well. But at this sort of crossing point, there's some drive now coming down from the kernel side. So we have a lot of buy-in from the kernel community who are pushing down. But we need to start really sort of standardizing this stuff from the hardware side up in terms of there are going to be specific types of software and specific loads which aren't specific to our NIC. they're going to be used across different types of NICs. And we almost need to start thinking about standards that can fit around those specific types of software loads, which are going to be very useful in specific use cases for OCP servers. And that was all I really wanted to get across today. Very short and simple. I'll be here. Anyone's got any questions, let me know. And I'll be outside afterwards as well. There's the throughput numbers in case you want them.
All right, thank you, Vic.